Hello everyone, now we continue our discussion of physics of semiconductor devices, and as I promised last time, we will start with surface recombination. It's necessary to highlight that because of band bending at the surface of a semiconductor sample or at the interface metal semiconductor, we observe some deviations of physical properties, in particular charge carrier concentration, in comparison to the bulk features of the semiconductor. Therefore, surface recombination, which also happens via deep traps, similar, like according to the Shockley Hall statistics, should also possess certain features which we highlight in this discussion. So we will consider a P-type semiconductor which forms some rectifying junction with metal, as shown on this slide. So here we keep so far everything in the dark and in thermal equilibrium. So we see that this junction is a rectifying one because as we come closer to the interface, this gap between top of the valence band and fermi energy level increases. That means that the majority charge carrier concentration in semiconductor decreases. At the same time, concentration of minority charge carriers increases, since the gap between fermi energy level and bottom of the conduction band as we approach interface becomes smaller. So this one. So here also we have energy level corresponding to the middle of the band gap, just to visualize and keep track of it. Also concentration of like energy level associated with some bulk trap in the bulk of the material, and here is energy level associated with a surface defect, which is of our interest in this discussion. So there is certain potential barrier because of band bending for holes, and it is equal to QVBI. So QVBI should be calculated, as we discussed last time, from the difference in work functions of the metal and semiconductor. So let us consider concentration of charge carriers in the bulk of the semiconductor in equilibrium condition, so majority charge carriers holes and minority charge carriers electrons. However, if we want to analyze quantitatively surface recombination, we need to know concentration of charge carriers exactly at this interface between metal and semiconductor. So in order to determine it, so we will denote it as NSO and PSO, so minority and majority charge carriers, electrons and holes concentration at the interface. So this will be minority charge carriers concentration in the bulk times this like exponent potential barrier, the amount of bending these bands, divided by kT. So that will give us concentration of minority charge carriers, like electrons, at the interface between metal and semiconductor, and majority charge carriers will be holes concentration inside the semiconductor times this exponent, but here will be minus because concentration of majority charge carriers decreases. It's smaller in comparison to the at the interface between metal and semiconductor in comparison to the bulk of the semiconductor. It's necessary to highlight here that the product of equilibrium charge carrier concentration, electron and holes, is equal to charge carrier in the bulk and at the interface between metal and semiconductor is equal to Ni square. So they are the same, doesn't matter. The values of each component here, like each term, will be different in the bulk and in the at the interface. However, their product will be the same. It will be equal to Ni square. So now let us disturb this system and push it out from the equilibrium condition. That can be done by shining some light, assuming that we have certain transparency of the metal layer, so it's semi-transparent, very thin metal layer on top of a semiconductor. When we shine light on a semiconductor, band bending. So if we have a rectifying junction between metal and semiconductor and shine light, this is equivalent to forward bias. So we will discuss this too in more details a bit later, but now you just need to know that the band bending in this case will reduce, and instead of QVBI we will have Q times VBI minus VOC. VOC stands for open circuit voltage. So band bending still will be there, but it will be smaller. And the other key difference is that instead of one Fermi energy level, we have now two quasi-Fermi levels for electrons and holes, because we have non-equilibrium charge carriers, like equilibrium plus non-equilibrium. So, in order to proceed further with the recombination at the interface between metal and semiconductor, we need to learn about charge carrier concentration, like total charge carrier concentration at the interface. So first we have non-equilibrium, like total equilibrium plus non-equilibrium charge carrier concentration given in the bulk of the semiconductor, where we don't have any band bending, in terms of quasi-Fermi energy levels for electrons and holes. So the same we can do for the surface, but we still need to take into account this residual band bending at the interface. So that's why we have concentration of minority charge carriers, like total concentration in the bulk times this exponent with argument where we have residual band bending divided by kT. For holes, at the total concentration of holes at the interface, we consider total concentration of holes in the bulk times this exponent with minus residual band bending divided by kT. Here it's necessary to underline that we are not in equilibrium condition anymore, and that's why this product of NP or NSPS, it will not be equal just to Ni square, but also need to take into account this open circuit voltage, Q VOC divided by kT, as an argument of exponential function, and that originates from the splitting between quasi-Fermi energy levels. So, taking this into account, we need to make another step, which is just a short recall of Shockley Hall recombination statistics, which we like this equation for net recombination rate U per unit time per unit volume, derived a few lectures ago. So there we have capture coefficients for electrons and holes. They are determined by capture cross section for electrons and holes and their thermal speed. Also bulk concentration of traps in the semiconductor, in the volume, like in the bulk of the semiconductor, concentration of total, like product of total concentration of electrons and holes, which are also have here equilibrium plus non-equilibrium Ni square, intrinsic charge carrier concentration, and here we have these parameters N1, P1, so they are equal to equilibrium charge carrier concentrations when Fermi energy level coincides with the trap energy level, which we try to quantify in terms of Shockley Hall recombination. So that is from our previous discussions, and now we have to adopt this to surface recombination, Shockley Hall recombination. First of all, we need to underline that this is recombination per net recombination rate per unit time per unit surface, not unit volume, because this is surface recombination, and that's why we deal here instead of bulk concentration of traps with surface concentration of traps. So we have units for NTS as centimeter minus second power. Here also we operate with surface total charge carrier concentration for electrons and holes, and respective capture coefficients for electrons and holes. So now, first of all, I want you to recall this equation which we discussed a few slides prior, and we have shown that this product of total charge carrier concentration, electrons and holes in the volume is equal to the same to that at the surface. So we can kind of interchange these guys with each other in our equation. So instead of NS times PS, we can write product for bulk values. It will be just N times P. Also, we need to recall that N total concentration of charge carriers is equal equilibrium, like electron concentration, plus non-equilibrium. Then total hole concentration is equilibrium hole concentration plus non-equilibrium hole concentration, and concentration of non-equilibrium electrons should be equal to concentration of equilibrium holes. Taking this all into account, we will get the final expression for net surface recombination rate, where we operate with like surface concentration of electrons, holes, equilibrium charge carrier concentration in the bulk, and this excessive non-equilibrium charge carrier, where we assume that delta N is equal to delta P. So in order to make this more practical, this term is usually named by surface recombination speed S, and once we know this parameter for a given surface, we can just multiply it by excessive non-equilibrium charge carrier concentration and get the net recombination rate. What is important to highlight that units for this surface recombination speed is centimeter per second, like really units of speed. That's why it's called surface recombination speed. So obviously this units for net surface recombination is different from net bulk recombination, and that's why we need to take some actions in order to unify the contribution of bulk and surface recombination in order to have some effective parameter which can take into account all of these features. So that's why we need to introduce some effective recombination lifetime. Assume that we have a semiconductor sample. So we form some contacts, for instance, to these sides of semiconductor sample, and this results in certain damage of the surface, so we get defects on the surface and surface recombination. Obviously we have some bulk recombination, which is bimolecular band-to-band recombination plus some trap-assisted recombination in the bulk. Both these bulk recombination processes can be described with certain recombination lifetime. So we can write here tau bimolecular plus tau Shockley Reed Hall in the bulk. When we want to take also into account contribution of surface recombination, because the result will be the same, we will just reduce concentration of charge carriers, and there will be less chance to collect them with these electrodes and extract in external electric circuit to do some useful work. So in order to take this into account and kind of normalize surface recombination also to the total recombination, we use this tau effective recombination lifetime, which should be determined as 1 divided by tau bimolecular plus 1 divided by tau Shockley Reed Hall plus 1 divided by and here we need to actually consider already not tau recombination like tau surface recombination, so we specify that here is in the bulk. Instead we can consider surface recombination speed divided by the thickness of this sample, like distance between two interfaces which participate in surface recombination, and since there are two of them, we can multiply this by a factor of 2. Not necessarily that both will participate in surface recombination, but if they do, then we have contributions from both. So in this case, we can determine this effective recombination lifetime, considering all possible mechanisms of recombination, bimolecular Shockley Reed Hall in the bulk and Shockley Reed Hall at the interface. Obviously that it will be smaller than the smallest recombination lifetime, because it will every new additional recombination mechanism will reduce effective recombination lifetime. So this is pretty much everything what I wanted to tell you about contact effect, like contact and surface effects in semiconductor devices. And we can proceed to further to one of the most important topic in the scope of our course, which is P-N junction. So contact as like of two different semiconductor materials with P-type and N-type, and this is actually considered as one of the most important building blocks of all type of semiconductor devices. So this is short list of our questions which we will cover during this first part of our discussion of P-N junction, when we determine the formation of P-N junction, distribution of space charge, electric field, and electrostatic potential, width of the depletion region, and its capacitance. So afterwards we will be ready to make one step further and derive equations for the current voltage characteristics of a P-N junction. So as I mentioned before, we will come back to this famous figure several times during the course, and I do hope that you will understand it and memorize it. So we start with intrinsic semiconductor, where Fermi energy level is located somewhere close to the middle of the band gap. But in order to make a variety of semiconductor devices, we need doping. So we have N-type and P-type dopings. So in the N-type, donor centers create some shallow energy levels in the band gap close to the bottom of the conduction band. Then thermal activation of electron from this energy level to the conduction band provides us with many free electrons in the conduction band, which can participate in charge transport. And as a result, Fermi energy level is shifted close to the bottom of the conduction band. So here we have expression for the equilibrium charge carrier concentration in such semiconductor, and also what is important for our further discussion, we have this depth of the location of Fermi energy with respect to the bottom of the conduction band. So here we operate with concentration of charge carriers like electrons, but if all donor centers are ionized, which is commonly the case, we can operate with just donor concentration of donors which are provided in the semiconductor. So similar happens with P-type doping. We have some energy levels created by electron acceptors close to the top of the valence band. So electrons are thermally activated, they occupy this energy level, and then we have holes remained in the valence band, which are positively charged charge carriers, and they can also carry electric charge and create form electric current in semiconductors. So as a result, the Fermi energy level is located close to the top of the valence band. So here are equation for concentration of holes in under equilibrium condition, and also the depth of the Fermi energy location in P-type semiconductor. So assuming that all acceptor centers are ionized, we can use here instead of P and A, which is total concentration of acceptors. So with this we can consider two semiconductors, P-type and N-type semiconductor. So here these blue spheres are considered as acceptors, and these small red pluses like free holes. So we have electrical neutrality. Every negative charge is compensated by positive charge. We assume that majority charge carriers, holes, in this p-type semiconductor is equal to concentration of acceptors, so all of them are ionized, and then minority charge carriers can be defined as Ni squared divided by Na. Similar we have for N-type semiconductor, so these red spheres, like positive charges, they are positively charged donors with concentration Nd, and this blue minus are negative charges carried by free electrons. So they also compensate each other. Concentration of majority charge carriers in the N-type semiconductor is equal to Nd, because all donor centers are thermally ionized. Here in the bottom part of the slide you can see a band diagram of these semiconductors before we put them together. So what do we have here? We have electron affinity, band gap, work function, the distance from the Fermi energy level to vacuum level, and also we can define this depth of the Fermi energy level location. So this is for p-type semiconductor. For n-type semiconductor, affinity, electron affinity, band gap, they will be the same, because this is the same material, the same semiconductor, just doped with donor and acceptor centers. However, work function will be smaller in this case, because Fermi energy level will be located closer to the bottom of the conduction band. And here we have the depth of the Fermi energy level location. So this is equilibrium condition when these two blocks of semiconductors with P and N type are separated from each other, and let's see what happens when we put them together. So obviously we have a lot of electrons in the N-type, a lot of holes in the P-type. So as a result, there will be some gradient of concentration of charge carriers. They will start to diffuse. So electrons from N-type diffuse to P-type, and electrons from P-type to N-type. What will be the destiny of these charge carriers? Once electron from N-type diffuses into P-type region, it becomes minority charge carrier and will be compensated by majority charge carriers within like very short interval of time. So it will be just neglected in terms of any other processes. The same will happen with holes from P-type semiconductor. When it diffuses to N-type, it will become minority charge carrier, and majority defines the behavior. So that's why minority charge carriers will be neglected. So the biggest mistake, and was one most common mistake when people try to explain the formation of a P-N junction, that space charges which are formed as a result of this diffusion, a negative space charge in the depletion region, like in the depletion region of P-type semiconductor, and positive space charge in the depletion region of N-type semiconductor. They are formed by these diffused electrons and holes respectively. That's not true. Once they diffuse, they just vanish there, and their contribution is negligible as minority charge carriers. So what indeed matters, these are negative and positive charges of acceptors and donors, which are fixed in crystalline lattice. They cannot move. So imagine initially we had electrical neutrality, then because of diffusion, electrons from N-type move to P-type, and we have some residual uncompensated positive charges of donors. So these fixed positive charges of donors, they create a space charge, positive space charge in N-type semiconductor, and uncompensated negative charges of acceptors when holes diffuse to N-type. They stay in this pre-interface region and also form a negative space charge. So the source of space charge in P-N junction is coming from positively charged donors, fixed, immobilized, and negatively charged acceptors. So this you need to remember. Obviously, if we create some space charge, this space charge creates electric field, so it will be oriented like internal electric field, which is oriented from N-type semiconductor to P-type semiconductor, and this will play a role in bending, because we will, with electric field, we also have some electrostatic potential distribution. So that how it will look like. So we have initially, like, and further, we always have plenty of holes in P-type semiconductor. They start to diffuse in N-type semiconductor, where we don't have many holes. The same happens for electrons. In the N-type semiconductor, we have many of them. They diffuse to P-type, where we have small concentration of electrons. However, because of this formation of internal electric field, due to the space charges formed by positively charged uncompensated acceptors and donors and negatively charged acceptors, there will be also internal electric field, as we mentioned. If we have electric field besides diffusion because of gradient of charge carrier concentration, we will also deal with drift current. So that will be drift of minority charge carriers, electrons from P-type to N-type, and holes from N-type to P-type. At some point, because of formation of this space charge, and internal electric field, which causes bending, we will form some potential barriers. Here we have potential barrier for electrons moving from N-type to P-type, and here we have potential barrier for holes moving from P-type to N-type. So they will reduce diffusion current and increase drift current. Eventually, when we have equilibrium, diffusion currents of majority charge carriers will be compensated by drift currents of minority charge carriers, and we will have zero, like net current flowing through this P-N junction, so it will be thermal equilibrium. So obviously, at some thermal equilibrium, as we discussed previously, Fermi energy level will be the same for both sides of the semiconductor. So now let us consider this height of the potential barrier, which is Q VBI. We know from previous discussion that it should be equal to the difference between work function. However, from this energy diagram, we can see that this height of the potential barrier is equal to band gap minus depth of Fermi energy location with respect to the top of valence band for P-type semiconductor, like here, and the same with respect to the bottom of the conduction band of N-type semiconductor. So that is actually this expression. we remember equations which we just recalled at the beginning for majority charge carrier, equilibrium charge carriers, which are equal to concentration of acceptors like in the P-type and donors in the N-type semiconductor. From these expressions we can get the depths of the Fermi energy location for P and N-type semiconductor, and it's defined by KT times natural logarithm NV divided by NA. For P-type semiconductor, where NV stands for effective density of states at the top of the conduction of the valence band, and for N-type semiconductor will be KT times natural logarithm of NC, effective density of states at the bottom of the conduction band, divided by ND. So here again I focus your attention and remind you that we assume all acceptor and donor centers thermally ionized at given temperature. So now when we substitute these expressions for delta EFP and delta EFN, we get finally the expression for height of the potential barrier, which is EG band gap minus two terms originated from P and N-type semiconductor. So first of all, we can increase height of the potential barrier by increasing concentration of acceptors and donors, means doping more. That makes sense because we will push Fermi energy level closer to the respective bands. So the these terms will be smaller. Then we will subtract smaller quantities from band gap, and our effective band gap will be larger. Sorry, not effective band gap, but potential barrier at the P-N junction. Other thing what we need to highlight, that with increase of temperature, we have here temperature here, we decrease potential barrier because we at higher temperature subtract larger quantities from band gap, and also we can see from here that the largest height of the potential barrier is actually the band gap for non-degenerated semiconductor. So if we don't have heavily doped semiconductors, which is not common in optoelectronics, this is true. The highest possible potential barrier is defined by the band gap. So now we need to discuss charge, density, electric field, and electrostatic potential profiles in P-N junction. So we will consider so-called abrupt symmetric P-N junction when we have uniform concentration of acceptors and donors, and it's not and they are equal to each other. So that's quite common in semiconductor materials, because we usually add some doping. They uniformly distribute in the volume of semiconductor and uniformly dope it. There is no some gradient of doping concentration. If that is necessary, then some additional technological steps are required. So we will start with Poissons equation, which gives the relationship between electric field and space charge. So the second derivative of electrostatic potential with negative sign over position is equal to first derivative of electric field over position, and that should be equal to space charge as a function of position divided by epsilon epsilon naught, which is the electric constant and permittivity of free space. So the net charge will be defined by positively charged donors, negatively charged free electrons, negatively charged like fixed acceptors, and mobile positively charged holes. Obviously that in the depletion, so we care about this within the depletion region, and taking into account this feature, we can simplify this expression for space charge, because in depletion region concentration of charge carriers is negligibly small, and we will have for P-type semiconductor just some square shape of space charge will be uniform in the N region and just go to 0 when we have a transition between depletion region and neutral region. So you can see here some dashed line that stands for some small deviation from this step shape because of diffusion of charge carriers from neutral region to depletion region. But that is very small contribution. That's why we can cancel out these effects of mobile charge carriers on the space charge and define it completely with acceptors, ionized acceptors and uncompensated in the P-type semiconductor with negative sign, and with positive sign ionized donors in the N-type semiconductor. So here I would like to draw your attention. We have this axis X, so we can define depletion region in the P-type semiconductor as X smaller than 0 and larger than minus WP. And in N-type it's larger than 0 and smaller than WN. So we have kind of two depletion regions in these semiconductors. These thicknesses will be the same because we assume that NA is equal to ND. So now obviously our next step is to calculate the electric field distribution in the depletion regions for N-type and P-type semiconductors. For this purpose we need to solve these differential equations considering some boundary conditions. So first boundary condition, that electric field at the edge of P-type depletion region, we have electric field equal to 0 at the coordinate x equal to minus omega p, and electric field at the edge of the N-type depletion region at the coordinate x equal wn also is equal to 0. So why? Because beyond depletion region we don't have any like space charge. We already in the neutral region. If we don't have space charge, there is no electric field. So that's why this is the origin for these boundary conditions. So we have this differential equation, I mean this one, and we integrated. These guys are constant. We don't don't need to integrate them. So this is the result of integration with some constant C1. We now use boundary condition, determine this constant, because at boundary condition electric field is equal to 0. Instead of x here we substitute minus omega p plus C1. So from here we determine C1 as constant and substitute it back in our solution. So that is the final expression for our case for the P-type semiconductor electric field in the depletion region at the coordinates x smaller than 0 and larger than minus WP. So we see that this is a linear function, so it means that electric field will linearly change in the depletion region. It will increase from 0 to some value. We will discuss this in short term. So for N-type semiconductor we have a similar procedure. We also solve this differential equation like by integration, get this integrating constant, consider respective boundary condition. From this boundary condition we determine this constant, substitute it back in our solution, and get the solution for electric field distribution as a function of position in the depletion region located in the N-type semiconductor. So this is also a linear function, so it linearly changes within this depletion region. So now we have these solutions for electric field distribution here, and here we have the graphical representation of electrical field distribution inside the depletion regions of the P-N junction. So obviously, because of this, there is not possible to have some discontinuity of electric field. At this point x equals 0, electric field from left and right side from P and N type regions should be the same. So then we can substitute x equals 0 in these equations and equate them for both sides, for P and N type. From here we get the following equation. It will be Na times Wp equal Nd times Wn. So what does it mean? If we increase concentration of acceptors, then the width of the depletion region in the P-type semiconductor should decrease because the product should remain constant. Why it happens? Because we should have electrical neutrality. So if we have certain space charge, positive space charge in the N-type semiconductor, and we need to have the same space charge in the P-type semiconductor. So if Na is increased, then we need thinner depletion region in the N-type semiconductor in order to reach the same magnitude of space charge which is in the N-type semiconductor. If concentration of acceptors is decreased, then as a result we need a wider depletion region in order to have in total in magnitude the same electric charge, which is different in sign, but in magnitude should be the same as that one in the N-type semiconductor. So with this I believe we finish for today. We discussed the formation of P-N junction and also discuss the space charge distribution and electric field distribution in a P-N junction. The next steps for us will be calculation of the electrostatic profile distribution in the P-N junction. So thank you very much for attention. See you next time, and we will continue our discussion of P-N, like properties and features of P-N junctions.